anyway, so in talking about this recursion theorem, one of the applications was about indices, and I did want to say a little bit more about this. So indices of sets, and we already saw some things, right? We have E, a sigma 0, 1 index for some set A was this described exactly the case where A is the domain of phi of E, and so a sigma 0, 1 index is just a particular way of describing a set, and this because it's in an index position in the expression, they say it's an index. E is a delta nut index for A if the characteristic function of A is equal to phi of E, and we have a pair E comma phi. It's a delta 1 index if A is equal to WE and the complement of A is equal to WI. And so those are for computable sets, you know that they have descriptions of all three forms. But we showed last time that from a sigma 0, 1 index you cannot effectively obtain a delta nut index, even though you know for any computable set there exists a delta nut index. There's just not a way of effectively changing one into the other, and that often restricts your abilities. The other indices, what do you know about those?
Well, delta 0 and delta 1 are the same, basically.
They're pretty close, right? They're different indices, but you can go back and forth between the two, and this is related to this theorem that a set is computable if it and its complement are computably enumerable. Of course, that statement says that, well, classically these two things are equivalent, but if you look at the proof of that statement, then you see that, well, it's clearly easy from a delta nut index to get a delta 1 index, because you first decide whether you're in or not, and then you diverge or not diverge with this information. And the other way around, the trick was, well, you start these two machines running, and you know that at least one of them holds on every input, and you just wait until the first one holds, and then you know whether the answer is yes or no. So the delta nut and the delta 1 index you can go effectively back and forth between. And obtaining from either of these indices a sigma 0, 1 index is also easy. But if all you have is a sigma 0, 1 index, then you can't effectively improve it. Now there are particular examples of sets which are even nicer than ordinary computable sets, and those are finite sets. And for finite sets we have some really nice indices too. Let's say I have this set x1 up to xn, a finite set, then we can represent this by a single number y. Right? There's of course many choices here, and you should hope that it doesn't matter which reasonable choice you pick. And reasonable is of course a fuzzy word, but I have nothing better to offer at this point. So certainly this is one way of having finite sets be represented by natural numbers. We actually picked some other ones earlier on with this effective pairing function and encoding into the exponents of prime factors. But this is a nice one because if you think about this one, and in particular if you imagine this being sort of ordered in an increasing way, then this y, so if you look at the binary expansion of y, it has a 1 in those places where there is a number in A, and so the binary expansion of y is an initial segment looked at in the right way of the characteristic function of the set A. Right? So in that sense, this one is sometimes nicer than other ones, but of course you can always go back and forth between them. This is called the canonical index for A. Right, and a canonical index for a finite set is really nice because given a canonical index for a finite set, you really know everything there is to know about the finite set. It is, for instance, very easy to see what the maximum number is. You just look write down the binary expansion of this number and see in which location the biggest one occurs. It's very easy to see how many numbers there are in this set, because you just do the binary expansion, see how many ones there are. So a canonical index for a finite set is really one where you have the finite set fully in hand, so to say. It's hard to imagine that there is information in the finite set which you don't have easily accessible in this representation of a finite set. So related to this notation, we use the notation d sub y for the finite set encoded by y. And of course any natural number encodes some finite set in this particular way. So related to our realizations about these indices before, now it would be really nice to have the theorem of the form that there is a partial computable function, let's call it phi I, such that if phi of x is the characteristic function of f, where f is finite, then phi I of x converges to a y where d of y is equal to f. Alright, this would be a really nice theorem which says that given a, what do we call it? Given a delta knot index of a set which happens to be finite, you can effectively extract from this a canonical index. I noticed a little bit of spacing because this would be nice, but it's false. There does not exist such a function. Right? So in the same way as for these computable versus computably enumerable sets, different indices really give you different information. Even though, of course, if you don't care about effectiveness requirements, then the statement is ridiculous. That different ways of representing a finite set are different, because if something is a finite set, then you can write it down as a listing, but it's just that you cannot, in an effective computable way, go from one of these representations to another one of these representations. And so these are the kind of things which in constructions later on you have to be careful with, because your classically trained mind is very quickly going to say, well, given a finite set, I'll list it and then I'll do my construction on the finite listing. You can't always do that, because this transformation cannot be performed effectively. Everybody happy with it? I'll prove it now, but right, what it means and why it is a little bit of a restriction of our joy in these kind of things. Yeah, but it's a nice theorem anyway, so we can prove something nice, even though we might be happier with the opposite theorem. Okay. Let's prove it then. Well, you can guess, of course, how this proof is gonna go. I have to show that something is not computable. Well, I guess so far I've only shown that things are not computable in two ways. One is assume it is computable, get a contradiction. The other is reduce something which I already know to be not computable to it. I'm not going to do a reduction here, so I'm going to start by saying, suppose there exists such a function phi I that given an index for a characteristic function of a finite set computes its canonical index. Suppose we have such a phi I, and then of course the first thing I'm going to do after that is define a different computable function using this computation phi I, which I'm going to use to get a contradiction. It's just about the standard pattern so far. Okay, what am I going to do? Well, what I want, of course, is this should be a valid input for phi I. So this phi of fn should be the characteristic function of a finite set, but we need to keep it nice and fuzzy which finite set this is in some sense. Right? If I just say it contains 0 and 1 and nothing else, then I have nothing used. So I want it fuzzy, and it should depend on phi of I, and so I'll let this be 0 if phi I x of n diverges. So this is to say, if the computation of phi I on input n, and n here is the input to my function f, you can kind of guess already that I'm going towards an application of the recursion theorem here. This n, I start my phi I running on this n. If after running this for x steps I have not converged yet, then on input x I output 0. I output 1 exactly when phi I x of x converges and phi I x minus 1 of x diverges. So I output a 1 exactly for that input, which gives me I output a 1 exactly for that input, which is the length of the computation of phi I on input n. And I output 0 otherwise. And yes, I'm fully aware that the first case is kind of superfluous with the last case, because but this is kind of how I think about this computation. You keep outputting 0 until you find the exact state at which it converges, then you output a 1, and from then on you always output zeros. So even though it's superfluous, it corresponds to a certain idea. And you certainly notice that phi of fn is the characteristic function of a finite set, because either phi I on n never converges, in which case you always output 0, and you're the characteristic function of the empty set, or you do converge, in which case there is exactly one length of how long it takes you to converge, and that length that length of how long it took you to converge is exactly the one element which is in the set. So the phi of Fn is either the characteristic function of a singleton function set or of an empty set. Both of which are empty, which is nice because this means we can use it as the input for our phi I. Well, we can use anything as an input for our phi I, but with our assumptions on phi I, it has to converge and give us some information. Anyway, before we do that, I now use the recursion theorem. Notice this function f is clearly a total computable function. I hope that you've thought about this thing long enough that you even agree with it clearly, not just that it's true, but that it's clearly a total computable function. Therefore, by the recursion theorem, there exists an n such that phi of n is equal to phi of Fn. So this here is the characteristic function of some finite set, and because it is the characteristic function of some finite set, we know that phi I of n converges. N is its canonical index. Right? We assume such a phi I exists. Phi I always converges on indices of finite sets. So this conversion, we can let S be the number of steps it took to converge. Right? So what does this mean? Our computation phi I on input n, it converges after exactly s steps. So this is a Turing machine. On input n, if you have n in unary on the tape, then you start computing, and after you finish computing, you now have some number y in unary on the tape, and this whole computation from the n in unary on the tape to the y in unary on the tape took s steps. Right? Now what do we notice? S is in d phi I of n, right? Because phi of n is equal to phi of f of n. Right? These characteristic functions are the same. Phi of f of n exactly gave 1 only on the length of the number of steps it took for phi of I on n to converge. And so this canonical index, maybe I should give it a name, this canonical index y is the canonical index for the singleton S set, the set containing only S. End of proof. Because we have a contradiction. What is our contradiction? Well, this set here, phi I of n, I guess I can write it. I said here, S is in there, but really I argued even more that this really is just singleton S, right? Because the characteristic function was either empty set or a singleton. I argued S is in there, so it's singleton S. So this means its canonical index is 2 to the S. Right? So this means phi I of n is equal to 2 to the S. There's a singleton in there. If you look at the definition of canonical indices, this canonical index is exactly 2 to the S. So now we managed to do a Turing computation of s steps long, and in those s steps we managed to write 2 to the s once on the tape. You can't do that. Right? In s steps, even if you're as efficient as you want to be about writing once on the tape, you cannot write more than s things on the tape. You cannot touch more than an s part of the tape. And so, in s steps, you cannot write 2 to the s on the tape. Therefore, this phi doesn't exist. It couldn't write 2 to the s on the tape in only s steps. Contradiction. And so now that we have this, now that we know that for finite sets there are also essentially different indices, or effectively essentially different indices, you can now quickly realize some other things, right? If I give you a delta knot index of a finite set, so I tell you, here is the index of a finite set, it's the delta knot index. What is its maximum element? It's a finite set, so certainly there exists a maximum element. However, you can't compute it, because if you have a delta knot index and you know what the maximum element is, then you just run through all the elements less than the maximum element, figure out exactly which elements are in the set, and you obtain the canonical index. So that's to say, from a delta knot index plus the information what the maximum element is, you can obtain the canonical index. You can't do that in general. Therefore, in general, you cannot extract what the maximum element is from a delta knot index. Good. Or bad, maybe. This is, I mean, it's true, so if you think it's bad, you need to readjust your intuitions. Any questions?
So, also, like, implicit in the contradiction is that if the Turing machine was going to do what it had to do in every case, it would have to already check if there's 2 to the s ones on the tape.
You need to read your input. Yes. I guess that's yes. If you don't read all of your input, then you can certainly not act appropriately. Because if you only read an initial segment of your input, then you can come up with a bigger input where you give the wrong output. Yes. Yes, because I did not argue, it might be the case that n is 2 to the s and you've already have the right output on there, but then you can't read your input, and therefore you could pad it to a longer input where you now give the wrong output. Yes, yes. I certainly didn't consider the case. It's kind of curious, right? Because the level at which you get a contradiction here really is... We haven't really reasoned about Turing machines in any proofs before like this. That's just how it is. Did I skip any other details? It's sometimes hard if you already know how it's supposed to go to really make sure you get all the details. Very honest one. Okay. Then one of the important questions, or I guess our big motivating question, or our big question this semester is, what does this collection of Turing degrees look like, right? We have the Turing degrees, we have Turing reducibility in nice order on them. What does it look like? Well, we have succeeded in showing that there is these two different things. There's the computable sets, and there's the holding problem, which is not computable. And by cardinality considerations, you get some more stuff, but we'd like to understand this situation a little more. And one of the attempts at understanding this a little bit more didn't quite succeed in the way it could have, but it gives us some nice characterizations anyway. So we'll talk about that for a moment. First, there's this definition. If R is 1 M or T, then we call some set R complete. If this set is computably enumerable, and W R reduces to A for all computably enumerable W. So given whichever reduction notion you care about in the moment, we restrict our attention to only the computably enumerable sets. And then this is exactly what you should expect for completeness. Something is complete if every other computable set reduces to this particular computably enumerable set. So that's what I mean with R completeness and Turing complete, one complete or many one complete, all defined in one fell swoop. And then we know already that K, K naught, and K1 are all one complete, and I clearly didn't prove all of those, but they're in the book somewhere. You should have read this, and none of the reductions are very difficult, really. You need the right idea. And so from this, it also follows that if we have 3 one-complete sets, then they all one reduce to each other, and we have Myhill's theorem, and Myhill's theorem says that if you have 2 sets which one reduce to each other, now of course these one reductions could be kind of badly behaved with respect to each other, but using a proof strategy similar to the Cantor, Schroeder, Bernstein, and whomever else you want to put in the theorem, you can get a permutation out of it. And so if you have 2 sets that one reduce to each other, then there exists a computable permutation which permutes the one set onto the other set. And this is kind of nice because things which differ by a computable permutation in some sense should be really considered computably the same. Right? They're really nice, the same of each other. And now what we're going to do for a little bit is come up with a nice reason or a nice strategy for proving that lots of other sets fall in the same category of being one complete and therefore differ from the holding problem by a computable permutation. Okay. Definition. P is productive if and only if there exists a partial computable psi such that for every x, if x is the index of a computably enumerable set such that this computably enumerable set is a subset of P. Of course, this is a complicated requirement in general. I didn't restrict the complexity of P at all, but even if P is relatively simple, then this is still a requirement about the infinitely many numbers in general, and so complicated. But if this happens, then it is the case that psi of x converges and psi of x is in P minus Wx. So a set that is productive is a reasonable way of looking at this definition is to say that a productive set is one which is effectively different from any computably enumerable set. If a computably enumerable set is not already different from it because it's not contained, then you can effectively find a witness that shows that this Wx is not all of that set. And the standard example is kind of k bar. K bar is productive. The complement of the halting problem is productive, and it's productive by a function psi, which is the identity function. And that is exactly the definition of k bar, right? Because if Wx is a subset of k bar, if you have some computably enumerable sets which is a subset of k bar, first I guess I should say, clearly no computably enumerable set is productive because it's equal to one of these then. So k bar at least has some hope because we know that it might even be the only set we know not to be computably enumerable. But as soon as there is Wx is a subset of k bar, that means that x should be in k bar minus Wx. This is supposed to be blindingly obvious. No, it is, yes, because being in k bar means exactly phi of x diverges, and I'm sorry, I'm completely blanking out on this. This is one of these things which is, I think, supposed to be in your face, right? If you look at it, you think of the right definition as the right time, then it's completely obvious, and I'm clearly failing a little bit. What do I really need to see? Well, I need to see that if Wx is a subset of k bar, then this happens, right? This is exactly the claim that the identity function is a production function for k bar. So, right, it's an implication. Assume this, prove that. I've reduced myself to pre-calculus now. Assume this, prove that. Well, what we want to see is that this thing diverges. Because as soon as it diverges, then we're done, right? Because this diverging means both that x is in k bar, and it means that x is not in wx. This same statement means both of these things. So this is all we need. So suppose not. I can think of anything better. And now it does become blindingly obvious. Because suppose not. Well, suppose not. That means that this converges, which means that x is in wx, but it also means x is in k, and so this subset relation is false. I told you there was nothing happening here other than the right definition at the right time. Everybody happy with that now? Or did I manage to sufficiently mess up the obvious to make it seem like it's complicated, difficult, and stuff? Anyway, let me argue again. So I need to see this implication is true. How do you show an implication is true? Well, assume the thing on the left-hand side, prove the thing on the right-hand side. Assume the thing on the left-hand side. Well, observe that even without that assumption, the right-hand side is equivalent to phi of x diverging. So we need to see that this inclusion implies that it diverges. So suppose you have this inclusion and it converges. Now we need a contradiction. But we have a contradiction because if this converges, then x is in wx, but x is also in k, so x is a counterexample to this inclusion. I don't know what else to say about it, because now that I see it again, I remembered it being blindingly obvious, that it was completely fuzzy for a while, but now that I see it again, it's again blindingly obvious, and I don't know what to say and explain anymore. So. Think about this long enough until you agree that it's blindingly obvious, and then we're all good. And if you fail at doing that, then you should ask me again, and I'll try to get halfway as confused as I was at the start of trying to prove this. So that's productive, but the more interesting notion is creative. C is creative if it's a computably enumerable set and C complement is productive. So this means C is equal to Wx for some x, but its complement is effectively different from any Wx. That's what creativity means. And by the proof that K is productive, and K bar is productive, and we know K to be CE, we know that K is creative. So a creative set is a CE set that is effectively non-computable. Might be able to prove this next theorem in the remaining 5 minutes. It falls apart in 2 nice parts anyway, so I can at least do one of them. So a set being productive means it has this productive function, but a priori the productive function can of course be pretty bad. It says here, it's a partial computable function which finds witnesses. Now for some of the things we want to do later with these productive functions, that's not good enough. So we want to show that anything which has such a function has a better one, and the exact statement is as follows. Any productive set P has a one-to-one total computable production function. So from this possibly crappy partial computable many-to-one production function, you can obtain one which is total and one-to-one. Which is nice because that's exactly what we have in our one example of a productive set so far. That was the identity function. The identity function certainly is total computable and one-to-one. Any other production function can be made to be equally nice to that function. So we do this in two steps. First, showing that a production function can be made total, and then once we have a total function, we'll make it one-to-one. I think the one-to-one, even though it's a little bit of technical work, is kind of there's kind of a clear idea involved in making it one-to-one, because right, as soon as you have Wx a subset of P, then you can start generating different RE subsets of P by adding this phi x to it. Right? This phi x is something which is outside of Wx, and so if you start with this, and then you take this set Wx union phi x, then you get a different set, which still satisfies the same requirement. Therefore, you can again apply the production function to get something outside of it. The thing which is outside of Wx union phi of x is certainly outside of Wx. So now you have two distinct witnesses for Wx. If those are not distinct from everything you've seen before, then you take Wx union these two distinct witnesses, still a subset, and you generate a third distinct witness. So what I've shown there is that I can make it one-to-one. Well, I lied a little bit, because of course if you need totality there, but you also, if this property is not true, and you cannot effectively check whether this property is true, if this property is not true, its image might not satisfy this. Its image might, for instance, just be in Wx. And then you wouldn't generate new things. But you can keep generating new images until either you start looping, and as soon as you start looping, you know that you were dealing with a set for which this property was not true, and so you can map it to an arbitrarily large enough thing. And if you never start looping, then you will always generate enough elements to find something different from what you had before. I don't know why I did that, because I was planning to start with a totality, but I guess I proved if you have a total production function, then you can make it one-one by these two ideas. So then all that remains is to take a partial production function and make it total. And so what is the only problem? Well, the only problem is that if Wx is not a subset of P, our function doesn't have to converge. And so we need a trick to deal with that. The trick is to define W of g of x equal to Wx if psi of x converges and empty otherwise. And you look at this definition and you need to convince it to take a second to convince yourself that what I wrote here makes sense, right? G of x is supposed to be the index of a Turing machine whose domain is W of g of x. So I need an index of a Turing machine which is either empty or equal to Wx. And so what do I do to get this Turing machine? Well, I start computing phi of x. If this never converges, then this case is false, so I'm in the otherwise case. In which case I need an index for the empty set, and I'm already doing the right thing, never converging. If on the other hand this thing does converge, then at the end of this thing converging, I can just run my Turing machine x and give the results exactly as Turing machine x does. So this is a good definition of a computably enumerable set. Even though I guess it's like our computable functions before, but with one extra level of definitions in there, because I wrote CE sets and not Turing machines. But that doesn't hurt us very much. And so the nice thing is, if W of x is a subset of P, then psi of x converges, and G of x is a different index for the same computably enumerable set. So, under the condition that x is one of the x's we care about for the production function, x and G of x are indices for the same function. If G of x is not equal to Wx, well, we didn't care about Wx anyway, because this always converges if we care about x. So now we can define our total function. Q of x is equal to psi of x or psi of G of x. Now that's of course a ridiculous definition, because these things are likely different. However, whichever converges first, right? If x is not the index of a Wx, which is a subset of P, then, well, we don't really care about the x except for the fact that we want to make it total. But in that case, we just need something which converges. Well, if psi of x doesn't converge, then W of G of x is the empty set, so now G of x is the index of a set that satisfies it, therefore psi of G of x converges. And notice the argument I just gave. If this does not converge, then that converges. So at least one of the two converges, and if both of them converge, then both of them are good answers. And I don't care which one I pick, but I'll just pick whichever converges first, because it's hard to wait for an event which might never happen. So this is indeed a total production function.